Good day, students. Today, let us look into the symmetry in crystals. Here is shown the pictures of a few crystals: gypsum, wolfenite, and halite. All these crystals, their shapes show symmetry in particular directions. They have a particular shape. This is because these crystals possess symmetry in each orientation. Now, the crystal symmetry determines the dynamics and the properties of that system. The symmetry is a tool to study the internal structure of crystals. Now, to know whether the crystal has symmetry or not, we do symmetry operations upon that system, upon that crystal. So, the symmetry operation is an operation that transforms the crystal to itself. That means, even after that operation, that crystal remains invariant. There are different types of symmetry operations. The first one is the point group symmetry operations. That is, the symmetry operations will be performed upon a point or a line. The other one is space group symmetry operations. Now, if we combine translation operation with any of the point group symmetry operations, we get space group symmetry operations. Now, let us go through each of the symmetry operations. The first one is translation operation. Now, in the picture shown here, the blue dots represent the lattice and the orange bigger dots represent the atoms in the lattice. Now, if these three atoms are made to translate along this fundamental vector, they will reach these positions in the lattice. Now, if we look at that atoms as a whole, there is no difference in its structure. Hence, symmetry is maintained in translation operation. Now, even if we translate these three atoms along another fundamental vector in this direction, the symmetry of that three atoms remains as such. Now, the next operation is a rotation operation. Now, consider the square with the central dot as the point of rotation, axis of rotation. Now, by rotating it by 45 degrees, we get this structure. Now, this is not similar to the earlier one. So, the crystal has changed. Now, if we rotate by 90 degrees, that is 2 pi by 4, we get the square shape again. That is, the crystal, if it was a square shaped crystal, it would remain invariant. And this shows that that crystal has four-fold rotation symmetry. We get the number 4 by the denominator used here to get 90 degree. 2 pi by n, that n value represents that n-fold rotation here. Now again, let us assume a triangle with the point of rotation or axis of rotation represented by the black dot. Rotating it by 30 degrees, it becomes as such. It is not similar to the earlier case. Rotating by 60 degree, we get it like this. Again, it is not similar to the first shape. Whereas rotation by 120 degrees, that is 2 pi by 3, we get the first shape again. So here, this triangle possesses a threefold rotation symmetry along the axis of rotation. Now, the rotation of theta, that is 2 pi by n, about an axis transforms the lattice to itself here. And the axis of rotation is said to have an n-fold rotation. Now, let us see all these shapes given here. Now, in the first shape, if we rotate this structure only by 360 degrees, do we get the same shape? That is 2 pi divided by 1. Hence, this has one-fold rotation. Now, taking the second shape, now rotating this shape upon this point, if we rotate it by 180 degree, we will get the invariant structure. That is 2 pi by 2. Hence, this shape shows two-fold rotation symmetry. Again, for this shape, if we rotate the shape at the central point here by an angle of 120 degree, yes, this remains invariant. Hence, it has three-fold rotation. Now, here in this shape, if we rotate the structure at the central point here by 90 degrees, this structure remains the same, that is by 2 pi by 4. Hence, it has four-fold rotation symmetry. Now, in this shape, if this structure is rotated by 60 degrees upon the central point, central axis of rotation, we get 2 pi by 6, that is 60 degrees. Hence, this has six-fold rotation symmetry. Now, usually in crystals, we have 1, 2, 3, 4, 6, etc. folds of rotation axes. 5-fold rotation and 7-fold rotation are mostly prohibited. But nowadays, we have designed crystals, quasi-crystals having 5-fold symmetries. Now again, in these two shapes, both of them have 6-fold rotation symmetry axes. Now the next symmetry operation is reflection operation. Here, reflection takes place at a plane in the lattice which divides the lattice to two identical halves. Now in this structure, the black line shows the lattice or crystal lattice and the blue line shows the plane of reflection. So on either side of the blue line, the plane of reflection, the lattice remains similar, right? It looks like a reflection of the other. Hence, this crystal has reflection symmetry along that plane. Now, assuming this structure, a square shape again, the plane of reflection divides this crystal into two identical halves. Hence, this crystal has plane of reflection along this plane. This crystal again has another plane of reflection perpendicular to the earlier one. This too divides the lattice into two identical halves. Now the next symmetry operation is the inversion operation. By this operation, we mean that each point at a random x, y, z coordinate from the lattice point will have an identical point at minus x, minus y, and minus z from that lattice point. So in this cubic structure, if we take the lattice point at the body center of that unit cell, exactly at the body center, for every x, y, z points on the unit cell, we have minus x, minus y, minus z lattice points having atoms in it. It is true in all the x, y, z positions. Now, in 3D lattice structures, in three-dimensional crystals, we have 32 point group symmetry operations. We mean that crystal can have a combination of point operations and that combination is called a point group. So here we have 32 crystallographic point groups in the 7 Bravais crystal systems. Now here we understand that for the triclinic crystal system we have one-fold rotation axis. And with the minus 1 we understand it has a inversion point along the one-fold rotation axis. Now for the monoclinic system, we have a two-fold rotation axis. We have a reflection plane. We have a combination of two-fold rotation axis and reflection along a plane perpendicular to the rotation axis. This bar represents that the reflection plane is perpendicular to the axis of rotation. So likewise, we have 32 point groups. Now, if we combine these point group operations with translation, we get the whole crystal. And as such, this group is called a space group. Now, the group of all the symmetry elements of the crystal structure forms the space group. Here, the point group operations combined with translation operation make the space group. And in three-dimensional lattice, there are 230 space groups. In two-dimensional lattice, Bravais classified the lattice into 5 systems, and it is given here. The 5 systems are the square system, hexagonal system, oblique system, rectangular primitive system, and rectangular centered system. Each of their lattice parameters are represented here. For two-dimensional system, we have lattice vectors A and B and interfacial angles gamma. The shapes of 5 of these crystal systems are shown here. In the square system, we have the lattice as such. In the hexagonal system, the lattice is shown as such. In the oblique system, the lattice will be formed as such. Here, gamma is not equal to 90 degree, but it is less than 90 degree. In the rectangular primitive system, here the crystal lattice is as such. And in the rectangular centered system, we have the crystal lattice as such. In three-dimensional space, the Bravais lattice was classified into 7 crystal systems, and they are the cubic crystal lattice, monoclinic crystal lattice, triclinic crystal lattice, tetragonal crystal lattice, orthogonal crystal lattice, rhombohedral or trigonal crystal lattice, and hexagonal crystal lattice. Each of their lattice parameters are defined here. To understand it, let's see. For a cubic system, imagine a cube and the dimensions along the 3 coordinates are the lattice vectors given as A, B and C. For a cube, all of these are equal, right? So we have A equals B equals C. And the angles between all of these 3 vectors is alpha, beta, gamma, 90 degrees. So we have a cube here. Now, when we elongate this cube along one particular axis, we get the tetragonal system. That is, A equals B, but it is not equal to C. Whereas alpha equals beta equals gamma is equal to 90 degrees. So an elongated cube along one axis represents a tetragonal system. And a cube that has different lengths, we can't say it is a cube, but the structure from the cube, we elongate that structure in all the 3 directions. That is, A will not be equal to B, will not be equal to C, whereas all the angles are 90 degree itself. That represents the orthogonal crystal system. So we have to keep a relation, we have to understand the relation between these lattice parameters to remember them. Further, examples for materials that crystallize into these different 7 crystal systems are shown here. So silver, sodium chloride, calcium fluoride, chromium chloride, calcium oxide, they show cubic crystal systems. Whereas magnesium sulfide, potassium nitrate, barium sulfate shows orthogonal crystal systems. Here, the 14 Bravais space lattices are represented. In the cubic structure itself, cubic crystal system itself, we have 3 types of unit cells. That is the simple cubic, the body-centered cubic unit cell, and the face-centered cubic unit cell. Next, in the tetragonal crystal system, we have the simple tetragonal unit cell and body-centered tetragonal unit cell. In the orthorhombic crystal system, we have the simple orthorhombic unit cell, end-centered orthorhombic unit cell, the body-centered orthorhombic unit cell, and the face-centered orthorhombic unit cell. In the monoclinic crystal system, we have the simple monoclinic unit cell and the end-centered monoclinic unit cell. In the triclinic crystal system, we have only the simple triclinic unit cell. In the rhombohedral crystal system, we have the simple rhombohedral unit cell. And last, in the hexagonal unit cell, we have the simple hexagonal unit cell. So all of these 14 space lattices are called the Bravais lattices. All of these 14 show symmetry and creates the periodicity in crystals. Now let us understand the symmetry elements in particularly within a cubic crystal. Now cube possesses an inversion symmetry, that is each point at a position R is relative to a lattice point to an identical point at minus R relative to that same lattice point. That means the cube has the body center lattice point, and from this point at any points at R and minus R you will be able to locate atoms in the lattice. Now in the next symmetry, the cube possesses reflection symmetry, that is, reflection symmetry exists. It exists if there is a plane in the lattice that divides it into two identical halves that are mirror images of each other. So, for a cube, we have three parallel planes. It is shown here. You have to draw it out. Now, in the picture shown, we can see that in the first cube, we have the top plane that represents a parallel plane. So parallel to this plane, we have the bottom plane. Okay, so if we take the shape of this unit cell on either side of this plane, we can see it remains similar. Again, with respect to this plane, if we see the neighborhood of that unit cell, it will remain same on either side. Now for the back plane, we can see that for repeated unit cells, the front portion of the unit cell will be identical to the back portion of that next unit cell. Along with that, we have 6 other diagonal planes in a cubic crystal, and it is shown here. Try to draw it out. In all these reflection planes, we can see that the either sides on the reflection plane will be identical. Now, cubic crystal has rotation symmetry. Now, it exists if its rotation by an angle about an axis transforms that lattice to itself. The angle will be an integral multiple of 2 pi. And we have the relation n theta will be equal to 2 pi, right? Even if we rotate it just single time, it will be equal to 360 degree, right? Again, if certain crystals are rotated by 90 degrees 4 times, it will be 360 degrees. So here the n represents that multiplicity, how much times I can multiply or rotate that particular axis. And n decides the fold of the axis. So for 4-fold rotation axis, it is called a tetrad axis where theta, the angle of rotation, is 90 degree. For a 3-fold rotation symmetry axis, it is called a triad axis, tri for 3, and the angle of rotation is 120 degree. And for a two-fold rotation symmetry axis, it is called a dyad axis, and the angle of rotation will be 180 degrees. A cube has three tetrad axes, four triad axes, and six dyad axes. Here we can see how to understand the different axes. Now the tetrad axis is represented by these red lines in this crystal. If we rotate the crystal by 90 degrees along any of these axes, we have three tetrad axes, 1, 2, and 3. We get symmetry, or the crystal remains invariant. Again, we have four triad axes. The four triad axes can be identified as such. One axis joining this point and this point. Second axis joining this point and this point. The third axis joining this point and this point. And the fourth axis joining this point and this point. So if we rotate the crystal by 120 degree by any of these axes, the cubic crystal remains same. Now we have six dyad axes. Now how do we identify it? Now let us take one of the edge of the unit cell and find the center of it. Again, if I take this edge of the unit cell and its center, and by joining these two centers, the line joining these two centers is one of the dyad axes. Similarly, the central point here, when joined to the central point here, creates the second dyad axis. Then the central point of this edge to the central point of this edge forms the third dyad axis. And the central point of this edge to the central point of this edge forms the fourth dyad axis. The central point of this edge to the central point of this edge forms the fifth dyad axis. And the central point of this axis to the central point of this edge forms the sixth dyad axis. And a rotation of 180 degree along any of these dyad axes makes the crystal invariant. So to summarize, we have one inversion symmetry, then three parallel plane reflection planes, six diagonal planes, three tetrad axes, four triad axes, and six dyad axes in a cubic crystal. So totally we have 23 symmetry elements in a cubic crystal. Now, let us look into some other types of symmetry operations, and one of them is the rotation inversion axis. Here, the crystal will remain invariant when rotation operation is done and it is followed by an inversion through that rotation axis. It is shown here. So let us assume the crystal has a structure. All these numbers and these colored points are within that structure. And let us rotate this structure by 180 degree. So then we get this structure. And the point of rotation, axis of rotation is at this point. Again, if we invert the structure through this point, we will get this structure, and it is similar to the first one. Hence, the structure possesses a rotation inversion axis. Crystals possess 1, 2, 3, 4, and 6-fold rotation inversion axis. Now, the next type of a symmetry operation is the screw axis. Here, rotation is combined with translation parallel to that rotation axis. For example, here in the figure, we have the 2, 1 axis. It is represented by that term Nm, where we have the 2 pi by n rotation followed by m by n translation parallel to the rotation axis. So in general, this structure will be rotated by 2 pi by n, and it will be translated by m by n factor. So by 2-1 axis, we mean that this structure is rotated by 2 pi by 2, that is 180 degrees, and it is translated by 1 by 2, half of the lattice vector. So the lattice vector is usually defined as the distance between two atoms, nearby atoms, right? And here it is rotated by 180 degree and translated along the rotation axis by half lattice vector. And this structure is achieved. We get the next lattice point, right? Hence, here it is having the 2-1 axis. Next is the glide plane. Now, a translation of T by 2 parallel to the reflection plane followed by the reflection across that plane forms that glide plane. So we have a translation of half lattice vector followed by a reflection across that plane to get the glide plane or glide plane symmetry operation. Now we have three types of glide planes, that is axial glide plane, diagonal glide plane and diamond glide plane. In the axial glide plane, the reflection plane is parallel to the crystallographic axis and it is translated along A by 2 or B by 2 or C by 2. Try to imagine it. Okay. So first, we try to identify the reflection plane in that structure and reflect it upon reflecting and translate that structure along any of the x, y or z axis by a distance of either a by 2, b by 2 or c by 2. And this forms the axial glide plane. Now in the diagonal glide plane, again we have a reflection plane, but the translation vector will be along the vector sum of any of the two vectors a by 2, b by 2 or c by 2. So we have the vector sum of a by 2 and b by 2, or the vector sum of b by 2 and c by 2, or the vector sum of a by 2 and c by 2. This will be along the diagonal of that crystal structure. So we will identify a reflection plane within that structure. We have similar reflection halves on either side, and then the structure is glided or translated along this vector sum. Now in the diamond glide plane, again here the translation component or the glide component is the vector sum of any two vectors of a by 4 or b by 4 or c by 4. So we take the vector sum of either a by 4 and b by 4, or vector sum of b by 4 and c by 4, or vector sum of a by 4 and c by 4, and translate the crystal lattice along that vector. And this forms the diamond glide plane. So with that, we have come across several symmetry operations that are possible within a crystal system. That's all for today. Thank you.